Panos Hadjinikolaou. I'm replacing Theo Zachariadis in running today's colloquium. We have the pleasure to have a speaker from the Cyprus Institute. So give me half a minute to briefly present today's speaker. Is Theodoros Christoudias, Associate Professor at the Climate and Atmosphere Research Center. He has obtained a BSc and a PhD in physics from Imperial College in London, UK. And he has been also a collaborator in the Fermi Lab in the US before joining the Cyprus Institute in around 2010. Yes? So since then, Theodoros Christoudias has been instrumental in developing our research and educational activities on the broader field of environmental sciences, focusing on Earth system modeling and regional atmospheric change with the use of high-performance computing. Currently, Theodoros, he's a steering group member of the IMAC consortium. This is an international multi-institutional consortium of global Earth system model IMAC. And he's also a principal investigator in the CERN cloud experiment. So I don't think you can check his CV in our website for more of his activities. So nothing else from myself rather than invite Theodoros to give us a hopefully interesting talk.
Thank you, Panos, and thank you all for being here today. So when Theodoros Zacharias asked me to present a talk in the Colloquium series, I thought of a subject that could reach across disciplines and perhaps try to tie all the different things that we're doing here at the Institute, or at least be relevant to people that do all the different things here at the Institute. So I picked this subject. It's something that we've been working on for a few months now, as joining this CERN cloud experiment measurements and the global modeling activities. So without further ado, I will start the presentation. So in the year 1054, Chinese astronomers reported the observation of a guest star. And I mean, I cannot read Chinese, but I'm told this is what this text is reporting there. And this is the first known documented observation of such a thing. And then a few hundred years later, in the year 1606, one of the assistants of Kepler, but always the PI gets the credit, again observed a new star in the sky, and they called it Stella Nova, which I think everyone understands what that means. And it's highlighted here. This is their logbook, their experimental logbook, and you can see N there stands for new. This is the appearance of a new star. So if we use a simulator to try and reproduce the appearance of the sky back in the observation over China, this is how the night sky would appear. So in the middle there, you can see this is the new star. It's quite bright if you compare it to the other stars. Even it's brighter than the moon. In fact, it was so bright that it could be seen during the day, and this lasted for about 2 years. So this was obviously an event of significance, of astronomical significance. And if we point our telescopes to that location today, this is what we see. This is known as the Crab Nebula. And you can see it in different wavelengths, so in different frequencies of light. So this is the Hubble telescope in optical wavelength, then Newton in ultraviolet. This is X-ray, the Chandra X-ray Observatory. So you can see that this looks like a big explosion in the sky, fireworks. So this is a combination of all the different wavelengths, if we could see across beyond human vision. And then for the other event that Kepler reported, again, if we point the telescope there, this is what we see. This is quite small in the sky. Its apparent magnitude or size is approximately equal to one of the moons of Jupiter, let's say. So it's a very small thing, but it's quite far away. But then to be able to radiate that much, obviously it was a big release of energy. And now we have a good theory of what happened there. So there is this phenomenon that is called supernova. I hope that most of you have already are at least somewhat familiar with this, but essentially what happens is that a star explodes, and the reason for that is, well, we have to look at how a star works in very basic terms. So a star is, there's huge mass, so it's pulled together by gravity, and it's producing a lot of heat because of thermonuclear fusion. So helium and hydrogen in its core is fusing to produce heavier elements, and that is releasing a large amount of energy that's sort of counteracting the gravity. And for very massive stars, let's say approximately more than 10 times the mass of the sun, because they burn up their fuel quickly, in the core, and this is not to scale, but deep in the core, you start creating this onion structure. So all these heavy elements start forming, and you can see you go hydrogen, helium, carbon. So as you go from the heavier elements reside in the center until you start producing iron. Now, iron cannot fuse anymore. It is the heaviest element that you can produce by joining nuclei together. Beyond that, it is not energetically favorable to join nuclei. So once you start producing a lot of iron in the core, you basically run out of things to fuse. And that means you stop releasing all this heat energy that was keeping the star alive. And when this happens, you have a massive implosion. So at an instance in time, these massive stars undergo core collapse, and basically it means they cannot produce enough energy to sustain their own size because they cannot counteract the massive forces of gravity. And this is quite spectacular because it happens in maybe a second or so. At most, it happens in a few seconds if the star is really massive. So if you imagine the size of a star, to have this thing happen, you release enormous amounts of energy. So the collapse happens in approximately a second, or even less than that. So the implosion happens in 70,000 kilometers per second. So this is the speed at which everything comes together. This is approximately a quarter of the speed of light. And all this infalling material bounces off this massive core that cannot be sort of pressured to shrink anymore, because there's no way you can fuse more elements. As this happens, you create an outward shock wave that causes everything around the star, so around the core, to explode. And this releases all the material into the interstellar medium. And it's so much energy that if you take all the stars in a galaxy combined, if you take all the stars of a galaxy like the Milky Way and join them and see how much they would radiate, this is how much energy is produced per unit time during this explosion. And then if the star is, depending on its mass and age or metallicity, that's how astronomers talk about star ages, this leaves behind either a neutron star or a black hole. And in fact, this is the main source of all the elements in the periodic table. So this is how all the mass that is around us is produced. And you might have heard this expression where we are stardust. So all of us originated, the material that is making everything around us and us is created or was created in at least one, or sometimes even there's the expectation that a lot of material undergoes multiple supernova explosions. So at the same time, this big release of energy, because it accelerates charged masses, it is one of the main sources of galactic cosmic rays. These are the very energetic and dangerous cosmic rays that are hitting the atmosphere. And it can generate very intense gamma ray bursts. So gamma rays are the sort of light in the highest frequency that can be sustained. So it's very energetic light rays, more energetic than X-rays. Okay, so this is what happens. So if a star dies, depending on the mass, it can create these huge explosions and create materials. Now, before we see what the consequences of that could be, let's try to define a couple of important parameters here. First of all, in astronomical distances is not convenient to use everyday measures to try and express them. So instead of using meters, astronomers define this new unit that they call parsec. This is short for parallel second, but it's pretty simple. It's not very involved. So if you take the distance between the sun and the Earth and create a triangle, so if the triangle on the angle that it creates is one of basically 1 second of a degree, the distance between the sun and the point of your triangle is defined as the parsec. So that's 1 parsec is equal to approximately the distance that light would cover if it traveled for 3¼ years, and is pretty much equivalent to 30 trillion kilometers. So the first supernova we talked about, the one that happened in 1054, that happened approximately 2,000 parsecs away from the Earth. Kepler supernova was a bit further away, it was 6,000 parsec. And just to give you a measure of distance, so the Milky Way edge to edge is approximately 40,000 parsecs, and the sun is around 8,000 parsecs from the center. In the center, we have this black hole that was Sagittarius A, that was imaged some time ago. So this is just to give you a brief sort of idea of where we are in the cosmos. But then this happened so far away, and they were so bright, and we have these huge explosions. But what if something like that were to happen nearby? Or equivalently, how close would something like that were to happen to have a significant impact on life on Earth? Now, it's estimated that we have 2 of these supernova happening in the Milky Way every century. We don't see all of them because some are hidden behind dust clouds, and we reside, the galaxy is pretty flat, so we reside on one of the arms, so we can observe everything that's happening on all the other arms. But it is possible that something like this could happen nearby, but perhaps more interesting to astronomers were, could this have happened in the past? Could this be linked to something like a mass extinction event? So there is evidence for a nearby supernova, of course, not in the written record like we saw in the Chinese astronomy. but there is this thing called the local bubble, and we don't talk about Cyprus now. We live in a bubble, but so around us, around the sun, there's a large span of space, which is around 1,000 light years in size, so like 300 parsec then, that is devoid of gas, that doesn't have a lot of material, if you compare it to just outside this bubble. Okay, so the theory is that initially it was thought at one, but now it's believed that maybe a cluster of supernova happened in the past that sort of blew out this material and emptied the space around our solar system. But perhaps even more convincing is these traces of an isotope of iron. Remember that iron is produced in the core of the supernova. And then there's this special type of iron called iron-60. It's a bit different in its structure of the nucleus. But this type of iron is not so stable as the other isotopes, and it has a half-life that is approximately 2.5 million years. So you could imagine after tens of millions of years, all this iron would disappear after being created. Now, if you look at the record of sentiments and see the sort of ratio of iron-60 over normal iron, you see that around 2.5 or maybe 3 million years ago, there is an excess. And this is seen on sediments on Earth, but also the same thing was seen on moon samples that the astronauts retrieved. So it's pretty clear that something deposited this iron at that time. In fact, there's another around 6 million years ago. It is believed that there's still another excess. So it's possible that every 2 or 3 million years, we have an explosion of a supernova that's nearby enough to deposit material on Earth. And as we said, there is if we take what astronomers assume to be the rate of explosions, which is 2 per century in the galaxy, just a rough approximation is that you expect to have one supernova every 2 to 4 million years in our neighborhood. Now, what is also maybe a bit disconcerting is that these things happen in clusters because stars in neighborhoods are created all together. And then, based on their size, they burn their fuel together. So it's more likely that you have bunches of this happening, or that you have this happening in regular periods. So it is possible that we'll have one of these, maybe not in the immediate future, but perhaps sooner than what we think might be the expectancy of life on Earth. Not our life, but of life in general. So that's something that we're very interested about, and there's a lot of people, particularly astronomers and theoretical physicists, that try to put some numbers on this, and oftentimes you see these papers with an exclamation mark in the end. Now, I was told by my PhD supervisor that if you see a paper with a question in the title, it probably means that the answer is no. But we cannot be sure, okay? So could a nearby supernova explosion have caused a mass extinction? Now, these people, they study supernova, they know a lot about the stars and the galaxies and cosmic rays, but ideally, it should be atmospheric scientists who can answer this question, because once this material reaches the Earth, we have to see how it interacts with the atmosphere, and if it could have these potentially catastrophic events. Now, the mechanisms that are postulated to create trouble on Earth after a supernova explosion, well, first of all, these galactic cosmic rays that would be produced in large numbers, and they would reach our planet. If they hit the atmosphere, they ionize the molecules, and they produce a lot of nitrous oxides. So NO and NO2 are molecules combining nitrogen and oxygen. Together, the atmospheric scientists call them NOx, and they have the potential to destroy the ozone layer up in the stratosphere. So in case anyone is not familiar with the ozone layer, so ozone is a trace gas in the atmosphere and is mostly prevalent in the stratosphere around 35 kilometers. You have a peak. There's some of it in the troposphere where on the lower level of the atmosphere where we live. It's toxic if we breathe it, but as you see there concentrations are parts per billion. In the stratosphere, we're talking about parts per million. So every million molecules, there's an ozone molecule. And it's usually measured in Dobson units. You might have heard this when people refer to the ozone hole. So the global average ozone is around 300 Dobson units. This is how many molecules you have per square centimeter. If you were to compact all that and create a sort of pure ozone gas at standard temperature pressure, so pretty much what we have on the surface, it would be about 3 millimeters in height. And then in the ozone hole, we have a destruction of that. It gets to about a third of that. So inside the polar vortices, it can go down to 1 millimeter or 100 Dobson units. And the reason it's important, and I'm sure everyone knows this, is that it absorbs most of the ultraviolet radiation from the sun. So if we plot the radiation reaching the atmosphere, and this is in energy units per area, we see that it's pretty much flat across a large band of wavelengths. And then anything below 300 is called UV, ultraviolet. We know this is very destructive. We know it's dangerous. That's why we put sunscreen in the, on the beach. But then you see that only a part of it reaches the surface, and everything else that is blocked, this is to do most of it is blocked by ozone. So if we were to destroy the ozone layer, we'd be irradiated with a lot of ultraviolet radiation. It would destroy our DNA and have a huge impact on the biosphere. The second thing that could happen in the atmosphere is another element that's called aerosols. These are in the condensed phase, so they're not gases. And there's this new particle formation in the atmosphere. Sometimes you hear that being called nucleation. So there we have individual molecules that are sort of bind together to form clusters, and they grow into bigger aerosol particles. And then some of them are coagulate to form even bigger particles. Some of them just evaporate. But if you have further growth, they can become cloud condensation nuclei. Now, in the atmosphere, you cannot condense clouds just from the vapor to the liquid phase. You need some sort of nucleus to condense on. And this is a very important process. And the galactic cosmic rays act as an accelerator of this process. So they really help these clusters stick together. So if you can imagine, if we increase the galactic cosmic ray flux on Earth by orders of magnitude, because a supernova would explode nearby, we could really accelerate this process and change the aerosol and cloud dynamics. So you might think this is a small effect, but actually this has two it has direct and indirect major consequences on the climate on Earth. So this is some figures I got from the IPCC, the Intergovernmental Panel on Climate Change. So in the top, you see how these cloud condensation nuclei that are formed by these clusters, they help create clouds, and it's estimated, there's a big uncertainty there, but it's estimated around 40 to 70% of all the cloud condensation nuclei are particles that have nucleated in the atmosphere. And this is an example of how clouds form on particles. You see the ship tracks, how these are clouds that form on ship tracks. I think this is off the coast of Spain or maybe the UK. So you have SO2 in the exhaust of ships. This creates sulfate particles, and then you have nucleation of aerosols, and these act as cloud condensation nuclei, and you create new clouds, and you can clearly see them following the clouds. And then they have indirect effects, and basically if you have more aerosol, you have more smaller droplets in the cloud, and because their size and curvature is different, this changes the reflectivity of the cloud. So if you have a lot smaller, more smaller and larger in number particles, you actually reflect more radiation. So, and also there is a theory that the clouds might actually live longer in that case. But this combined effect of aerosol-cloud interactions is a major radiative forcing agent in the atmosphere. There's a lot of aerosol produced because of human anthropogenic activity of human emissions. And also, it's not well known how the situation was before we had the sort of industrialization. So you see, this has an overall cooling effect in the climate, but you see the band, the black line signifies the uncertainty of that effect. So this is the change in effective radiative forcing from pre-industrial times until today. So you see, for example, carbon dioxide is having a net positive effect. So that's like heating the atmosphere. So these aerosols, through aerosol cloud interactions, which is the light blue, and aerosol radiation, are shown here. And this is actually the largest uncertainty in climate change. So it's important to understand all the processes I just described, not purely if, to know if a supernova were to happen, it would have dire consequences, but because this is the way to understand and really quantify the effect that humans are having on the climate. So this we can do with a lot of experiments. I would like to highlight the cloud experiment at CERN. So this is an experiment that tries to really study at the fundamental level the process of nucleation and growth of aerosols. Is actually a 20 cubic meter steel chamber, which is very, very clean air. It's probably the cleanest air on Earth. It has very little contaminants. And then it has, we can control humidity inside, as well as the relative concentration of the vapors that join to produce new particles. And then it's located at CERN because the CERN beam allows us to simulate the galactic cosmic ray and to ionize. Also, it has an electric field that can be turned on and off, so we can remove completely the ions and see run a control experiment. And also it has these lights, so you can illuminate it with UV and try to emulate the different conditions throughout the atmosphere. So the Cyprus Institute is a member of Cloud, and we joined since 2020. And of course, what I showed was a simplification. The real picture of cloud aerosol interactions is more like this and even more complicated than this. So you have all these processes. So it's nice to know things at the fundamental level, but ultimately to really capture the effect on the Earth system, you need to include all of these processes inside a detailed calculation. And we do that using model simulation. So we use global atmospheric models. So we have the Earth, we split it into little boxes, little grids. Inside each grid box, we have equations describing all the processes that I've just went through, and we have all the agents that can influence the atmosphere, the climate, and the composition. We solve these equations over time, so we integrate this rate of change of things over time to see the evolution of the climate. And here at the Cyprus Institute, we use a global model that's called EMAC. This is short for ECAM5, which is the circulation model that's originates from Germany. MESI is sort of a layer that sits on top that allows us to add all these components. So MESI was initially developed at our partners at Max Planck. We joined and we are founding members of the consortium that oversees the development and evolution of this model in 2010. And it is a modular system that allows us to plug in different components. It has state-of-the-art chemistry, as well as all the aerosol macrophysics that we just talked about. And it goes all the way from the bottom of the ocean to the top of the stratosphere. So it allows us to do simulations up to 80 kilometers height. And in spatial resolution, the whole globe is, we have 100 to 200 kilometers grid box size. And of course, you cannot run a model of this complexity on a laptop, so we run this on the Cyprus Institute high-performance computing facility. So inside MESI, we want to add all these, and we have added all these processes. So if we have a supernova that happens nearby, we have gamma rays and cosmic rays hitting the atmosphere. These create nitrous and hydrogen oxides that can destroy ozone and allow harmful UV radiation to pass through. At the same time, we have to simulate the process of ionization that allows nucleation to happen, to produce cloud condensation nuclei, and then study the impact of the clouds onto the climate. So if we had a supernova nearby, we could expect the galactic cosmic rays, the flux on the Earth to increase by a factor of 100. And so this is the present day ion pair production in the atmosphere. So this goes from the South Pole to the North Pole, and this is like an average of the state of the atmosphere from the surface all the way to 80 kilometers. And we measure height in pressure coordinates here. Now you might notice this is not exactly linear. This is because the Earth has a strong magnetic field. So it's hard for ions to penetrate in tropical latitudes. It's much easier to penetrate around the poles. So we multiply that by a factor of 100. So we have around 5,000 ion pairs created per cubic centimeter per second. That's quite significant, from 40, that is now present day maximum. And each ion pair in our simulation produces approximately 1¼ NO molecules and 2 OH molecules. And these are the things that enter into the complex ozone chemistry and have the potential to destroy ozone. So if we look in our simulation, how much more NOx we are producing, so this is a ratio to our everyday simulation that we call control, and you see that it goes all the way up to a factor of 30 in concentration, so we have 30 times greater concentration of NOx in the atmosphere. And then if you look at OH plus HO2, which is the equivalent for the hydrogen oxides, this is actually reduced in the stratosphere and is somewhat increased in the troposphere. So this chemistry and the ozone chemistry is quite complex, is highly non-linear. But overall, if we run a simulation and compare to a normal day, so this is the state of ozone in an Earth that's been irradiated by supernova galactic cosmic rays at a factor of 100 greater than every day. So you see that, okay, we have ozone production in the close to the surface, but remember, ozone there was much lower than the ozone in the stratosphere, and in fact it was the ozone in the stratosphere that was protecting us. So there we do see a decrease, but it doesn't seem to be really to the degree that would jeopardize life on Earth. So even though we increased the cosmic ray production by a factor of 100, we only have a small decrease in ozone. And then if we were to see it throughout the year, so now we have south to north pole on the vertical axis, and these are months of the year. The numbers here are in Dobson units, the present day ozone concentrations. So you can see in a world without an ozone hole, I should say. And so you see again that it might go down to 30 or 40%, but this mostly happens in the poles, and this happens when you have the creation of the polar vortices. And in fact, this situation looks very similar to the ozone hole that humans have created on Earth. So overall, the strong magnetic field of the Earth shields us from this, from the consequences of this radiation. Also, there's a reaction here that basically depletes NO, and this limits how much you can deplete ozone. And actually, in certain cases, you can even produce ozone through the HOX cycle. You remember we saw that HOX actually goes down. So overall, if you balance everything, it looks like the Earth is safe in that regard. But you might ask, okay, that's fine now, but you know, the Earth did not always have oxygen levels to the, that we have today, the oxygen levels that we have today. So we simulated an Earth with a 2% oxygen. This happened around 500 million years ago, and this is the early Paleozoic era, when you had this explosion of life forms on Earth. So you could imagine with a lower oxygen level, that would mean much lower ozone. So if you have the compounding effect of a supernova, maybe that would really jeopardize the creation or the sort of evolution of life on Earth. But again, we see, first of all, okay, we do have lower ozone in a lower oxygen atmosphere, and you see it's down to 80 in the tropics from 300, that is present day. Still, that was enough to shield life during its creation and sort of evolution on land. And again, we see a decrease that's more significant, but it's limited over the polar regions. So again, we can expect that life would survive such an event. Now, for the nucleation and creation of clouds, the situation is a little bit more complex. So the ion chemistry in the atmosphere is basically captured by this diagram. This is very complex to include in a global model along with all the other processes. So we selected the more sort of primary paths that cause this ion cascade. So we have here on the left the input of cosmic rays. In the end, we have these HSO4 ions that are the ions that help with nucleation. So we create a sort of system in equilibrium, and this we can describe with a set of ODEs describing the chemical kinetics, and we solve that and can estimate, based on the initial cosmic ray input, how much HSO4 minus we will have in the atmosphere. And it's quite important here to take into account that once you have producing many more ions, like we expect, then it's much more probable that they will hit upon one another. So if we go from 40 to 400, it's much more likely that they will recombine. So some of them, just because there are so many, are neutralized that way. So ion recombination, so this is the effect of 100 times GCR on the HSO4 concentration. So this is the ratio of the supernova over the present day conditions. So you see that, especially in the higher parts of the atmosphere, you can expect to have not now 100 times more ions as the cosmic rays come in, but only maybe a factor of 8 or 10 or maybe 15. But then if you take all the aerosol microphysics into account that we discussed about previously, the actual aerosol concentration ratio is much lower. So you only have maybe a factor of 4 or 5 greater aerosol. And I should also point out here that you don't really have a lot of aerosol in the upper atmosphere. So it would be more significant if it was lower down, where you have life or a lot of the clouds being created. So if we plug everything into our climate model, let's see now what is the change in the cloud condensation nuclei, these nuclei that clouds develop on. So this is a plot of the concentration of CCN, and we look at this at 0.2% supersaturation at cloud base. This is just a fancy way of saying this cloud condensation nuclei will only evolve into clouds if there's relative humidity in the atmosphere. So if you have a nucleus in a dry area, you don't have enough humidity to form a cloud. And we look at the cloud's base height in the model. Again, you have to be in an area where you can create clouds. So this is how it looks. And then this is the fractional change compared to present levels. Now you see in places we might have actually 100% change in CCN, which sounds significant. But if you look at the two plots combined, you see that the big changes happen in areas where you had very few CCN to begin with, and this is not a linear scale. So it's a very muted response of the climate system to the intense ionization, and this is due to the shorter ion lifetimes because of the recombination effect, but also that you have more particles competing for these condensable vapors to grow. So this ultimately slows the overall growth and renders them more susceptible to scavenging by pre-existing particles. And then if we see the effect of that on the radiative forcing, which describes how much energy is entering or leaving the climate system and ultimately is a measure of the climate change. So this is, on the left-hand side, the outgoing shortwave solar radiation at the top of the atmosphere, and again, the difference to present day. So you see that it's less than 20% overall, and it's patchy limited, is not always positive or negative. If we break that out into different latitudes, you see that you have a cooling effect in the tropical latitudes, and more of a warming effect in the poles. But overall, the radiative forcing between shortwave and longwave, so the net change in the Earth system is about minus 2.5 watts per square meter on the top of the atmosphere. So since energy is leaving the system, we'll have a cooling effect. Now, the magnitude is comparable to present-day climate change since the pre-industrial area, which though it's concerning, is not at the level that would really wipe out life on Earth. So to summarize, we have used the IMAG Earth system model based on parameterizations derived from the cloud experiment at CERN to try to study an extreme event of having the Earth irradiated by a massive increase of galactic cosmic rays. And this could happen because of a nearby supernova explosion. And we find that overall there's a mild effect on the biosphere, primarily at high latitudes. Mass extinctions caused by such an event would be unlikely. It would have to coincide with maybe a reversal or a diminishing of the magnetic field on Earth, which is highly unlikely. We see that the overall ozone loss is comparable to the present-day polar ozone hole from the emissions, anthropogenic emissions, and the radioactive forcing is similar to what we have now inflicted on the climate. So the good news is that my PhD advisor was right. So the Earth's atmosphere is really resilient to nearby supernovae. So the terrestrial life on Earth, life on Earth-like exoplanets could evolve over billion-year timescales, provided they have a magnetic field. So again, since now we're looking on life on planets beyond our own, this is a sort of good indication that is quite likely that once life sort of begins or happens, then it might be quite resilient to cosmic events. So that's all I have for you today. Thank you.
Thank you very much, Theo, for this exciting journey from these powerful objects in the star down to our Earth's atmosphere and climate. Let's take a couple of questions from the audience. We have also some online participation. If there is any question, they will inform us. Do you have anything you want to ask? Can I ask the simulations on the effects in the atmosphere, for how long did you run them? For example, you compare the 2.5 minus radiative force, which is comparable in the absolute magnitude of the global warming. But this is going on for a few decades. So how long does it take to reach these values in your simulation?
So we ran a full year that you saw in the graph here, but we also ran spin-out years. And then to be sure that the Earth system under these conditions are stable, we keep the simulations running for at least 5 or 6 years after this to be sure that we don't have net production of ozone or any other component that would create the imbalance, and also check year on year. Now, it would be nice to run this for tens or hundreds of years to be sure, but again, that is a bit, we're already running this at the level of complexity that was unprecedented. So all the other studies that I showed previously used 2D models or even very simplistic box model calculations of the effect. So this is the first time that such a complex model is involved. Now, we have confidence that our results should be robust exactly because we haven't shocked the system that much. So because the magnitudes are at 10%, it's likely that the equilibrium is reached, so we don't really are off balance in the climate system.
So, yeah, I was wondering about the complexity of the model in the other studies. So actually, this is the most comprehensive Earth system simulation.
Yeah, I think this is the first time that we run a 3D model, so not just a column model or a box model which simulates the whole atmosphere as a little box, a little cell. And it's the first time we have such a, not only all the cloud microphysics and complex aerosol dynamics, but also we have the aerosol, the ion cascade included. that as we've seen, has really a big effect on the actual ion lifetime, and that limits itself the impacts. A lot of the other studies, they just take a factor of 100 throughout the atmosphere, and they assume, so that means 100 times more NO, for example, or 100 times more aerosols. In fact, I think this is the only study that includes the indirect and direct and indirect effect of aerosols through nucleation and new particle formation. A lot of the studies signify that that's a big uncertainty, and I think we've shown that this is no longer a big concern.
I don't want to keep talking myself, but a last question, a more general, is compared to the older studies about connecting previous supernova with mass extinctions, could this model setup be used to test against such a theory? Is it necessary? Is it worth it? So, I mean, we used a model that's tuned to present-day conditions. Of course, we did the sensitivity test that's shown here at 2% oxygen. That covers already a large range of effects. Now, one could be very pedantic and try to go to, let's say, having a description of the Earth system exactly as it was 500 million years ago. Now, that in itself has a large uncertainty, but I think given our results and the fact that the major things that, so the cloud microphysics are relevant, and then we have the geomagnetic field in place, I wouldn't expect to have a big difference if you were to run this with a paleoclimate model or something of that sort. In any case, those models are much more simplistic because they run for thousands of years. Okay, so it contributes to that maybe debate, perhaps, these results, hopefully. So you are probably planning to share this in the scientific community?
Yeah, we want to, I mean, we are running a few other sensitivity tests. We're also simulating a direct hit by gamma ray burst, so a prompt burst of gamma rays that would, say, increase the energy flux on the Earth's atmosphere factor of 10. Also, there is the idea that if we're really close, maybe the X-rays radiated from supernovae can influence us. We'll see if, how much of that, maybe with a sensitivity test, is important, and then we want to publish this, yeah.
Okay, great. If no one else wants to add something about Konstantin Drovrolis would like to.
I'm wondering whether the advisor was wrong. So, I mean, whether you get mass extinctions. I mean, mass extinctions. Other people have shown that they can be the result of cascaded phenomena where you start with something very small that is regional, and that can affect an ecosystem that can create like a domino effect where eventually you can have a mass extinction. So, because in your simulations you see some regional phenomena, I mean, there is impact, even in this particular plot, right? There is impact
in the polar regions.
In the polar region. So, I mean, that part of your conclusions I would like to hear you elaborate a little bit. I think you're saying because we don't see major effects in specific latitudes, and we conclude that there can be no mass extinctions.
So I think if I understand your correction, you're talking about maybe tipping points in the climate system, or okay. So the reason we are saying there's not likely, from example this plot, a mass extinction event is because unfortunately we run the same experiment in our planet by destroying the ozone through emissions. So we know what happens if you have a sort of depletion of ozone in the polar vortex, which, by the way, disappears after you have the breakout of the vortex year on year. Also, remember that there's not a lot of life on the poles anyway. So most of the life evolved and is sort of reproducing on the tropics, but also these mass extinction events we're talking about not really affecting the population and sort of diversity of life on Earth. So both of these experiments, reducing the ozone or changing the climate within minus or plus 2 watts per square meter, we are unfortunately doing today. Now, it has consequences, obviously, but a mass extinction is not what that is. So I think that's why also what the other studies have sort of postulated is that you had a complete destruction of the ozone layer for hundreds of years everywhere. And that would say, you have UV rays destroying DNA, basically. Now, this could happen, but you'd need the supernova to be so close, say within 10 parsecs or less, which is, I don't want to say astronomically unlikely, because it's even less than that. So, I mean, even the studies themselves, they don't consider that a possibility. Now, could we have missed something? I mean, that's the unknown unknowns, but I think exactly because both the ozone loss over the poles and the climate change to about a degree or so we have happened in the last 50 years, that's what gives us a bit of confidence. Plus, those are not the things that the other studies postulate, that this will have a tipping effect, or they postulate a complete destruction of the ozone layer that would really expose life on Earth to high-intensity UV rays.
Thank you very much.
Okay. Yes, Camille.
Really inspiring talk. So you showed the graph of the estimated times of the supernova explosions, if I get it correctly, in the beginning, right? So do we know any timings for and the amount of the extinction events that we are talking about?
So there is at least 2 extinction events that have been linked with the possibility of a supernova happening at a close, now we're talking about millions of years now, but I think at least one is sort of, the scientists think that it's highly likely that it could have happened during a supernova event. Now, if this had a compounding effect, or if it had any effect at all, it's hard to know.
Thank you.
Last question.
This might be a bit trivial, but a supernova, a core collapse of a supernova would probably generate gravitational waves as well.
Yes.
Would they propagate up to us, and would that have an effect on climate?
So there is gravity waves in the atmosphere, but they're nothing to do with the gravitational waves that happen during supernova explosions. So we do detect gravity waves from perceived creation of black holes through, or neutron stars, I think, through supernova explosions, but they would have no meaningful or any effect on the climate. They are so, I mean, if they happen nearby, they would just distort space-time a little bit, but not really have an effect on us.
Okay, it's over 5 o'clock, and it's a very good time to say to Theodoros Christouzias, thank you again for this very interesting presentation.
Thank you.